In this video, we're going to consider chilled water design strategies for chilled beam projects. So here's the main layout. We're going to have a chiller plant, pumping system. Notice that for this slide and all the other slides, we're going to show you a variable primary flow chilled water plant. You could do this with primary, secondary as well. It won't matter to the overall discussion, but because it's variable primary flow, you can see we have a bypass that's controlled to maintain the minimum flow rate through the evaporators of the chillers. And then down here, we have a chilled water loop that's servicing the primary air handling units. Usually this water has to be close to 42 or 44 degrees Fahrenheit because it has to do the dehumidification in the air handling units up above. We're showing two coils here. That just think of it as two air handling units. It's not like there's two coils in series. But this loop is about providing water cold enough to do the building dehumidification. Now, chilled beams themselves are dry devices, which means the chilled water that's sent out to those beams has to be above the dew point of the space. And typically the design condition is 57 or 58 degrees Fahrenheit. So you can see that there is a second loop over here that is looking at the chilled water that's flowing out to the chilled beams. These here will be the chilled beams. There's their flow control valves, and this water is coming in at 57 degrees and going out at 64. And at a high level, you can see that the air handling units are on the kind of a primary loop, and then there's a secondary loop here that is servicing the chilled beams themselves. Now, in that last slide, we saw that we used a control valve to separate the two water temperature loops, the 42 to 44 degree loop for the air handling units and the 57 degree loop for the chilled beams. You could easily do that with a heat exchanger. We're going to show you this slide once here, but for the rest of them, you'll see us using a mixing valve. Either will work. It really just depends on your preference and your comfort level. So let's talk a little bit about the control. So the chiller plant would be set up through the chiller controls to deliver the water temperature for the lowest temperature you need. That's going to be the air handling units, right? So we're showing 42 degrees here. Could be 44, could be 40, whatever the design requirements. And that water is used to do the dehumidification in the air handling units. So you can see the primary air handling units are getting 42 degrees. The control for the secondary loop that goes to the chilled beams, in this case, we're using a temperature sensor on the supply water to the chilled beams, and it's modulating how much chilled 42 degree water is being introduced to this loop to cool it down to 57. So typically the return water temperature on chilled beams is about 64, 65 degrees, somewhere in that range. And so that water comes back, we mix it with some 42 degree water to deliver 57 degree water to the space. If this was a heat exchanger application, you'd still have a supply water temperature sensor, but it would be modulating the flow through the heat exchanger to deliver the right temperature to the space. On the, we've talked about temperature, let's talk about flow. So we have a pump, it's going to be a variable speed pump. We're using two-way valves out at all the chilled beam control zones. And a typical way to do this would be to put a pressure sensor in the piping system. Good practice would be at least 2/3 of the way out to measure that pressure and speed up or slow down the pump to maintain system pressure. So as these two-way valves open and the cooling load increasing in the building, the valves open to service that load, the pressure would start to drop, the pumps would speed up to build the pressure back up and increase the flow rate out to the chilled beams. Reverse is true. As the load drops off, these valves start to close at the control zones, and then what happens is the pressure starts to build up. That signal comes back and tells the VFD to slow the pumps down. An alternative way to do this would be if you had position indicators through a building automation system of all your valve positions. This is actually a more advanced and a more energy efficient way to do it. If the building automation system is polling all the control zones in the building, all it needs to do is maintain enough pressure to make sure that the zone that has its valve open the most is the one that's being serviced. So rather than just looking at the general pressure of the supply water piping system, we'd actually looking at valve positions. So you'd typically say that any valve anywhere in the building gets close to, say, 90% open, that you would start to increase the pressure so that the valves don't go fully open and that they lose control. Up here, let's talk a little bit about what's going on in the main loop that's servicing the air handling units. So again, you could put a pressure transducer near the pressure indicator near the air handling units and maintain the pressure for this loop. Again, as the air handling units require more chilled water, their two-way valves will open. They'll require more flow. That'll drop the pressure, because that'll send a signal to the primary pumps to speed up and increase the flow out to the air handling units. Reverse would be true if the load starts to drop off in the air handling units. These valves will close, the pressure builds up, and that causes the pumps to slow down. And again, you could do the same thing. You could look at the position of these valves and make sure that none of these valves get more than 90% open. If they start to get close to that, then you increase the flow. If they start to get a lot more closed and they're throttling down, then you can drop back the pressure and slow the pumps down. Now, this system is a variable primary flow system, so they're going to be monitoring the flow or the pressure drop across the chillers to maintain minimum evaporator flow rate. And at some point, that would open up the bypass here so that we would maintain a minimum flow in this loop through the evaporator as a way to avoid going laminar and heat exchangers and causing chiller issues. If this is a primary-secondary plant, you wouldn't be having this. You would have a bypass, but you wouldn't have this level of control. This part in here is all specific to whether you're primary-secondary or whether you're variable primary flow, which is what's shown here. Let's talk a little bit about chilled water reset. It's a well-known energy savings methodology in a building that if the conditions are right, that the cooling loads are lower and the dry bulb or the dehumidification requirements allow, you could actually try resetting the chilled water temperature up from the design conditions. And that's particularly attractive because as the weather moves around into the fall or an early spring, you've got a chiller plant that's making 42-degree water. The beams only need 57-degree water. Chilled beam system would appear to be a system that would benefit greatly from being able to raise the chilled water temperature during lighter loads for the energy savings. As you raise the chilled water temperature off of the chiller plant, you'll get a significant improvement on your COP of the chiller plant. So it is something to consider. But you also have to remember how important it is to have good dehumidification control in your building. Remember that all the dehumidification for the whole building will happen in these air handling units. And so the chilled water temperature really has to be prioritized by the need to dehumidify. If you can dehumidify the air with warmer water, you should do it. But often that water temperature is picked to create a leaving air condition off of these coils to maintain the right humidity level in the space. And so I would caution you to be very careful about this thing and really think it through before you do it, because you do have to maintain that flow. And any savings you get by resetting the chilled water temperature, if you can't do the cooling, then all the local cooling devices are going to respond by, hey, you're giving me warmer water. I can't get the cooling done in my zone, so I'm going to open my chilled water valve and I'm going to consume more water. So while you may be saving energy up here in your refrigeration plants because they can make warmer water, which is easier, you may actually spend that energy over here increasing the flow rates out to all the devices, and so you got to be really careful how you do that. And ultimately, the most important thing is to maintain good dehumidification control at your primary air handling units. So you can consider resetting this temperature if you're going to try a reset algorithm and start raising this from 42 to perhaps even 57 degrees based on the position of the valves. if you have a set point in here and you can monitor and control your supply air dew point, right? That's the important part, that this air has been dried out enough, not just its dry bulb temperature. And you can control that, start raising the temperature and then watching the flow. And if what you find here that this valve starts to go wide open, and because it's trying desperately to cool the air down enough to dehumidify it, that will help you have the information you need about how much reset you can get. Another way to consider doing this thing would be, first you slow down the pumps with an algorithm, and then you would start to do the chilled water. So let me show you what that might look like. So here we have a chart. You can see that this is the chilled water temperature in here, where we could be talking about a reset, and over here we've got the pump speed. And what we're going to do is we're going to look at the most critical valve. It's going to be one of the primary air handling unit valves, and we're going to monitor, if you have 2 or 3 air handling units, we're going to monitor the chilled water valves at all those units and consider the one that's trying the hardest to dehumidify. And so at first what we would do is we would maintain our 42-degree water, and we would allow the pump speed to modulate back and forth based on the load in the building. But as we get down closer to, let's say, 70%, the next step, what we could do is to say, okay, we're actually going to hold the pump speed even here, and then we will modulate the chilled water temperature instead to take the load off of the chillers for this lower flow rate in here. And this will work well. It helps you solve the problem of, do you want to send out a little bit of very cold water or a whole bunch of warmer water, and you've got to decide where you want your savings, from the pump or from the chiller. This is an algorithm that allows the programmer for the building automation system to decide how to do that. You just got to remember that in here, as you start to reset this temperature, you have to do it in such a way that you maintain your dew point in the space. So another thing we wanted to talk about is resetting, is to look not at the air handling units here, but let's talk about the chill beams for a second over here. Now normally we would send out 57-degree water. That's above the dew point in the space. It should, if the system's designed properly, that water temperature will be enough to do all the sensible cooling out in the space, which is all the chill beams will do. But what happens if we start to see a humidity climb? Something's gone out of specification or unexpected event, and we're starting to get the humidity so high in the space that the dew point in the space meets or exceeds the 57-degree chilled water temperature that we're sending out. And that would mean that the moisture in the air would start to condense on any exposed chilled water piping, and it would start to condense on the chiller, the coils that are actually in the chill beams. This is a very serious situation. It's not supposed to happen, but if it does, we need to have a response in the building controls to deal with that. And you can do things like, if you see high humidity in a zone, you could actually just shut these valves off and kill the flow to that chilled beam so it doesn't sweat. But if you do that, you are turning off the air conditioning in a control zone that is now probably hot and humid and probably needs air conditioning more than ever. You won't condense and sweat in the space, but you're also providing no cooling relief to the occupants. A different sequence would be to say, okay, something is amiss. Something is not happening the way we expect it to. We can see the start of high dew point in the space through dew point sensors. And this time, rather, what we're going to do is we now know that the dew point has climbed above 57 degrees. It's 58 or 59. We measure that, and we reset this chilled water temperature to be 1 degree above whatever we see in the space. So if this is gone from 57 to 58 dew point, then we take 58 degrees plus 1 and reset our supply temperature just to the chill beams, not to the air handling units, just to the beams, and keep this water temperature above the dew point. That's going to do a couple of things for you. First, it's going to mean that you won't have any condensation because the chilled water is staying above the dew point. And secondly, you'll get some level of cooling. Now, absolutely, if you raise your chilled water temperature, you're going to lose capacity at your beams, but some flow of warmer water is better than no flow at all. And so this would allow some relief to the occupants in the space. It does mean that you need to have dew point sensors in the space. You might not necessarily do this at the zone level. You might want to do this on a per floor or a large area. And if you start to see high dew point anywhere on the area that's serviced by this chilled beam loop, then you could start to reset the temperature in that space to avoid a condensation issue and having to close the valves off entirely. I spent a lot of time talking about how you would size the chillers in the chiller plant or how many chillers you would have. Most chilled beam projects are large enough that you're going to have multiple chillers, and that those chillers would typically be put in parallel arrangement like you're seeing here. Alternatively, you might want to consider looking at putting them in series. This is a nice arrangement. If you have a large delta T across your plant, it can actually improve the efficiency of the chillers, and something you might want to consider. And it's a nice segue into something that we talk a lot about with chilled beam plant design, which is if you look at it and you look at the water we need to go and do the air handling units where we have to do the dehumidification, the water that's coming back, the return water from the air handling units, is pretty close to the supply water temperature that you would need out at the chilled beams. And so the conversation comes around to, hey, could I take my water and flow it through the air handling units first, and then after that, take that water, run it out through my chill beams, which are sensitive, and I need the water temperature to be above the dew point of the space. And then I would get a very large delta T across the plant, which is really helpful for improving the chiller plant design. And it's particularly helpful around the hydronic system in terms of sizing the pumps and the piping sizing throughout the building. Well, we've modified the temperatures here so that they work out ideally. So we've gone to 44 degree water. There's nothing unusual about that. And we're going to design these coils so that in our air handling units that at design conditions, we will heat that water from 44 to 57 as we cool and dehumidify that primary air. Well, 57 degrees is the supply water temperature that we want to send out to the chilled beams. And so really quickly you would say, wow, this looks really promising, right? We can flow the water first through one application and then in series, right? Run that water over and through the chill beams and bring it back and have a very nice 20 degree delta T across the plant. Well, this is only going to work if your chill beam flow exceeds your air handling flow. And this is so important to slow down, stop, and look at your flow rates that we're going to walk through an example together so you appreciate it. Now, we think this is a good idea, that it should definitely be considered in your chilled plant design for chilled beams, but we want you to appreciate the care that has to go into this and the understanding particularly about how well your system works or how it will behave at part load conditions. And so there's a couple of things we want to talk about loads. The first one is, I want to remind you that this load is going to behave very specifically. This is dehumidifying and cooling outside air. And so the load on this system, this loop that serves the air handling units, is really proportional to your outside air conditions, particularly your enthalpy. And so as it cools off in the fall and into winter, this load will linearly follow that load outside. This load is about internal heat gains. And so yes, as the weather changes outside, it's going to impact heat gains through the wall, but you're still going to have solar heat gain, and you will definitely have all your internal heat gains, your plug loads, your people loads, your lighting loads. They're all going to add on. And so this load, as you go from design summer conditions through the winter and all the 4 seasons, this load is going to behave differently than this load. And you have to remember that. You have to think through all the steps. The second thing is, if we were talking about a fan coil system and the ventilation unit for it, roughly speaking, the ventilation is going to be 20% of your building load. Now that, of course, changes a lot depending on whether or not you're talking about a K-12 school or in an office building, which have a lot different ventilation load requirements. But whatever it is, the ventilation load is going to be noticeably smaller than the internal heat gains in the space. That is not true when it comes to chill beams for a couple of reasons. Mostly that this air that we send in is actually helping with the air conditioning load. You don't have to do it this way, but most systems are designed to deliver 55 degree air to the space, and that helps with the load. It probably is going to do a third of the cooling in the zone. The other 2/3 will be picked up at the chilled water here. So you're shifting internal heat gain loads to the here. Something you want to remember. And then the second part about it is, we run more ventilation air through these things than you would in, say, a VRF or a 4-pipe fan coil system, because we need enough air to make the beams work properly and to be able to do the dehumidification. So if you step back and add up your loads to your air handling units and you look at the tonnage that you need for the beams, they're going to be pretty close to being on par. They're certainly not going to be 4 to 1 apart. This is going to be roughly 50% and this is going to be roughly 50%. Completely depends on your location and the building application, but they're much closer to being on par. So I want to put flows on. So we saw that the temperatures just worked great, but let's put the flows on, right? So we're going to say we have a 100-ton load here and a 100-ton load here. And to meet that 100-ton load, 50 tons in our 2 air handling units, to heat that water from 44 to 57, will require 185 GPM. Straightforward calculation. So we're going to run that water through the 2 coils. We're going to heat that 185 GPM from 44 to 57. So by the time I get in this pipe right here, I've got 185 GPM of 57 degree water. Now set that aside for a second. Let's go look at what's going on inside the chill beam loop. Now I have 100 tons of chill beams out here, but I have a much smaller delta T across these. We're going to heat that water from 57 to 64 as we cool the space down. And you can back into that number and you're going to realize that this pump is pumping 343 GPM for this tonnage. And so you can see the flow rates instantly don't line up. So now what happens? So what happens here is we are going to put, at this point in the pipe, we have 185 GPM. It's got to go somewhere, so it's going to continue along this line. But we're actually going to add another 55 GPM to it, so that when we get to here, it's 240 GPM, right? 85 plus 55 is 240. This 55 GPM water is at 44 degrees, so it's going to cool the temperature down a little bit from 57 to a little bit less. And when we do that, we will need some return water here because we got to get all the way up to 343 GPM. And we need a little bit of heat to offset this cooler water that's coming in because we want 57 degrees. This is just a balanced flow calculation. And when you do it, you're going to work out you need 103 GPM of 64 degree water to mix with 240 GPM of water that's slightly less than 57 is going to deliver 343 GPM of 57 degree water to the space. This system is going to work fine. There are no issues. And there's no issues as long as this flow in here is always greater than this flow over here, which is actually likely what's going to happen in your building. But this is the part where you need to stop, look at your building, think through how it's going to behave in different seasons to make sure you don't get surprised, right? Because this flow comes down, goes through here, it's in series, it comes around through this mixing valve in here where we're going to modulate how much of this is coming down here and is being mixed with this. And so that rule about saying, hey, this flow rate always has to be greater than this flow rate is just to get the system to behave well from a flow rate point of view, not from a temperature point of view. Now this load, as we said before, is going to vary quickly with outside air. So as you go from design summer day to design winter day, this load's going to drop off. This one will drop off as well, but a lot slower than this one will because the internal heat gains are more universal across that. So if your flow rates are good on a design day, you're already well on your way to being able to convince yourself that you could do this kind of system design because this flow rate will be above the air handling unit flow rate during shoulder weather. Once the outside air temperature gets to the dew point of the supply air condition, there won't be any chilled water flowing through here. And all the water you need will come down through here and be mixed in here. And at that point, you can start talking about resetting the supply air temperature to do it. Or as we will talk about in another video, you can start looking at waterside free cooling. Now, I've shown you how it's supposed to work. Let me break it for you so you appreciate what would happen if things go the wrong way. And to do that, I'm going to switch the loads. I'm going to leave this at 100 tons, but I'm going to drop this load to 50 tons. Now, we saw before that if this is a 100-ton load at the air handling units, we would heat water from 44 to 57, and we would create 185 GPM of 57 degree water. That makes sense. But this load has dropped off significantly for some reason. And now what happens is you only need 171 GPM to meet the 50 tons of load of 57 degree water. So we'll heat that water from 57 to 64. It'll be 171 GPM. that seems fine from a temperature point of view. Have a look at what it's doing to your flow rates. At this point in the pipe, you have 185 GPM. You only need 57 degree water. You only need 171 GPM of that water right here because it's 57 degrees. So what should happen is you would take 171 GPM of that flow, send it out through here. You don't have to mix anything from anywhere else. Run it through your chill beams and send it back. And so there'd be zero flow through this return line here. Your problem is you got 185 GPM in this pipe, and you're only going to, this valve is going to pinch down and only let 171 GPM through here. And when you do that, you're now going to lose control here because obviously this valve is going to be able to block this pipe. And what will happen here is that you will not be able to get the 185 GPM you need through these coils. This one, these valves will open, but this one will close. And so you will not be able to do the dehumidification. What happened in here was we broke the rule, right? Now what's happened is that the chill beam flow is less than the air handling unit flow. So you really need to not just look at how the temperatures are going to work in your water system. You need to slow down and have a good look at how your flow rates, and not just on a design day, but you really need to spot it at, let's say, 50 and 25% load, remembering that these loads behave quite differently as the weather changes outside. And convince yourself that your flows are going to work well. Now, this system that we're showing you here is a good system. It does require this rule not to be broken. And for most cases, that's quite possible, but you do need to check your actual system design. So that was part one of chill beam or chiller plant designs for chill beams. Hope you enjoyed it. And if you want to see some other details, watch part two. Thank you very much.